If you remember, we did everything in terms of x, right? We had vertical representative rectangles that were dx wide, all the functions of the integrand, everything was in terms of x. But then at the very end last time I said, what about if we decided to use horizontal representative rectangles instead of those vertical representative rectangles? You know, how would that change things? And if I use those, these would all be dy thick. Wouldn't you think that if this really was valid, shouldn't I get the exact same answer? Shouldn't I get 4/3? So let's figure out what happens here if I do it this way. I'll just do this off to the side. Let's review integral. The limits of the integral. Can anybody describe like what the limits of the integral are telling us as far as finding the area? It's where you start and end the accumulation. Agreed. So I'm going to start down here at the bottom. So what would I put in for my lower limit? Yep, I'm going to start accumulating at 0. And where am I going to stop? At y equals 4. That's right. So if I've got these horizontal representative rectangles, I accumulate from bottom to top instead of left to right. So then the thickness of each representative rectangle is dy. And so now what I've got to do is I've got to put my integrand in there. And this is where sometimes it can be a little confusing because when we use x's, we're talking about top minus bottom for the integrand. Top minus bottom doesn't really work when you're doing like horizontal representative rectangles because there's always like one more representative rectangle above the one you're thinking about. And so instead of a top minus bottom concept, what do you guys think? What would it be? It'd be right minus left. Couldn't you say like from a relationship standpoint, couldn't you say that right is to top as left is to bottom? All the numbers to the right are higher, just like all the numbers to the top are higher. So I'm going to go right minus left, but here's where you could run into some issues. If I did right minus left and I put in this, I'm going to have a bit of an issue, right? For lots of reasons. Namely, everything has to be y's. Okay. So then what could I do to maybe rename these functions a little bit? Solve for x. There you go. So this one, the curvy one used to be y equals x squared. And so I'm going to square root both sides. When I do, it's going to be plus or minus root y is equal to x. And then the other one's a little bit simpler. It used to be y equals 2x. And so when I solve for x, it would be y over 2 equals x. Make sense? So then what do I do with that plus minus thing? Do I pick the plus or the minus? Because it's got to be one or the other. Why does it have to be plus? First quadrant. We're talking about the right side of this parabola. So you're right. Yeah, it is the plus. So it's going to be right minus left. So it'd be positive root y minus y over 2. So if this is valid, this should end up with the exact same answer. Let's see if it works out that way. So the antiderivative of root y would be 2/3 y to the 3/2. And the antiderivative of y over 2 would be what? Yeah, 1/4 y squared. And we will try to evaluate this from 0 to 4. So I plug in a 4, be 2/3 times 4 to the 3/2 minus 1/4 times 4 squared. And then thankfully when you plug in a 0 for both of those y's, bless you, you do get just a 0. So every now and then we have struggles with this. What is 4 to the 3/2? 8, that's right. So that would be 16/3 minus 1/4 of 16 is 4. And look at that, 16/3 minus 12/3. Maybe it really is valid, right? So the whole point of this is really simple. It just gets you to realize that integrating with respect to y is totally valid, just as valid as integrating with respect to x. There will be times when one is better than the other. There will be times like this one where you could go either way, and it really doesn't matter. You just need to make sure that what you're doing is logical, makes sense, defendable. You should be in good shape. Do you have any questions? Good. So I'm going to let you guys try number 5 by yourselves. For number 5? Well, if you're worried about graphs, I don't think the calculator is going to help you. Because your calculator, for the most part, most calculators, I mean, this is not true of Desmos, but calculators you can use, they're going to only graph functions. So let me help you with the graph here, and then I'll let you guys try this on your own.
Wait, so can you use a calculator, guys?
I don't think so. Like a TI will only graph functions.
If you subtract the other ones, just
And the first one's not a function.
Can't you graph the y using the... No, I'm saying...
There are some programs you can use, like the inequality, to do stuff like that. Yep. But I don't know. They'd probably just give you a graph on this one.
area better.
But we don't... So, how do we know which...
I'm going to help you graph it.
Oh, okay.
Hey guys, let me help you graph this really quick. Unless you run an inequality program, you're not going to be able to switch between outputs and inputs and all that stuff. So with this, hey guys, let me just ask you this question. In pre-calc, did you guys do much of this? Graphing where x was in terms of y instead of y in terms of x? I don't know if you did too much of this. Okay. Well, let's take a look. This one is the harder one. The other one's actually pretty easy. X equals 3 minus y squared. Isn't that parabolic? But instead of an up-down opening parabola, this is a left-right opening parabola. Would you guess that it opens to the right or to the left? It opens to the left because of the minus y squared. And then what about this 3, this positive 3? Shifted right 3. That's right. So this parabola would... something like that. This opening left, shifted right 3. And then, to be perfectly honest with you, if you're struggling with graphing that one, why not just write it in slope-intercept form and get y equals x minus 1? So that would look... something like that. So can you guys see this area okay? Does that look good? Okay, so let me turn you loose on that. Let's see if you can find the exact area of that.
Would it be any, like, less valid on this one either to use your radical?
That's part of your decision. Johnny.
What tells you that you're going to use the right side, not the left side?
It tells you that you're going to use the right side, not the left side.
I mean, like, what tells you that? Because like,
What tells you what?
that you're not going to be using the left side.
What do you mean by the left?
Like,
Oh, gotcha. Like over here?
yeah.
Oh, so it says, find the region of the area bounded by. So bounded is like a boundary, right? So that means there needs to be a boundary around your region. And I would say this region you've proposed has no boundary to the left. Like if it's truly a region that has a boundary, you should not be able to walk in any direction and get out without climbing over a wall. And so if you're in that region right there, you cannot get out unless you cross a red wall or a blue wall. But the one you're proposing, you could just keep walking left forever. You never run into a wall.
It makes sense and easier with infinity. Why can't we do that?
Yeah, it'd be awesome. Like, well, I counted to infinity, so I'm out. I'm the smartest man alive.
So we have to graph that and then...
Yeah.
So to find like what y coordinates or x coordinates we want to use.
Yep. Yep.
We can graph it in that way.
Oh, you mean like on your calculator?
Yeah.
No, you can do it totally on paper. 100% on paper. You could definitely do this without a calculator. Because you know how to deal with quadratics, right? Like if one of them was like y to the 5th, and there was like a sign of something or other, then we'd have to use a calculator. But based on the nature of these functions, you could definitely...
We can set them equal to each other, right?
Yep. Substitution, for sure, like you said. But that's better. Let's talk about why that's better. Hey, please listen up. You guys figured out that if you do these representative rectangles horizontally, you accumulate from bottom to top. Did you notice that in every single instance there, isn't the right edge determined by the blue curve and the left edge determined by the red line?
Yeah.
So because that relationship is consistent for the whole region, this is just going to require one integral. Let's talk about why that's better. If you decided to go with a vertical representative rectangle, you could. All of these are really good. In fact, I would say all the way up to right about here, all the representative rectangles on the top are determined by the red line, and the bottom is determined by the blue parabola, right? But then as soon as you get over into this part, doesn't that relationship change? Now, isn't the top determined by the upper part of the parabola, and now the bottom is determined by the lower part of the parabola? Because that relationship changed right about there where I put that little dotted line, you'd have to have a separate integral in addition to all the extra solving that you'd have to do. To me, that makes this way worse, not because it doesn't work, but simply because it's going to take you a lot longer, take a lot more parts, a lot more math that you might accidentally mess up, right? And so I'd rather you keep it simple and do it the simpler way. Does that seem reasonable? Okay. So let's do that. So if I did use a horizontal representative rectangle for that consistent relationship, going to integrate from bottom to top or accumulate from bottom to top. So I'm going to integrate from somewhere to somewhere, and it's going to be a dy. How do we figure out the somewhere to somewhere? Like, where do we start and where do we stop?
They're equal to each other. So
Yeah.
solve for y.
Equal to each other, solve for y. Aren't we looking for those intersection points? So I like your idea, Noah, of setting them equal to each other. So 3 minus y squared equals y plus 1. I'd go 0 equals y squared plus y minus 2. So by that zero factor property, I get y equals negative 2, y equals 1. Hey, conversation havers, that make sense? Okay, so negative 2 to 1. And then whenever you're using a horizontal representative rectangle, you want to go right minus left to maintain that positive dimension on the rectangle. So right minus left would be parabola minus line. And that would be your setup right there. Make sense? Okay. To be honest with you, I think I'd simplify this a little bit before I got busy with integrands and antiderivatives. What do we have? Negative y squared minus y plus 2. I think if you simplify that. And then we just move into the antiderivatives. Would be negative 1/3 y cubed minus 1/2 y squared plus 2y. Evaluated from negative 2 to 1. And then I plug in the 1, I plug in the negative 2, subtract in that order. So if I plug in the 1, it's going to be negative 1/3 minus 1/2 plus 2. And if I plug in the negative 2, what do I get here? 8/3 minus 1/2 minus 4. So what do we have? Negative 2, 6, negative 5, 6 plus, so 7, 6 minus, it would be 16, 6 minus 3, 6, that's 13, 6. No, I messed that up. Let's try that again. Say again? I don't know, did I mess something up? Oh, yeah. I think I plugged in a 1 again. Let's see here. There we go. So that would just be minus 2. Minus 4. So let's try that. So 16, 6 minus 12, 6 is 4, 6 minus 24, 6. It's negative 26. So minus 20 over 6. That's really plus. So I got 27/6. And that reduces to 9/2. There we go. So it was right, Ben.
Nice. Yeah.
Which is 4.5. John.
So I flipped the equation in the very beginning, but I got negative 27 out of 6.
Yep.
So can I just chop away that?
Let's talk about that as a group. It's good. Hey, Johnny, hey, listen. Johnny just asked a question that potentially applies to every single one of us in here. So check this out. Hey, you want to see this. This would be a silly reason to lose points. Hey, check this out. This could happen to any of us. So what if you started off with this original integrand? Let's say you tracked with it. You're like, yeah, I'm going to use y's and -2 and 1 for my limits. But what if, for whatever reason, you flipped around your integrand? What if you exchanged those? Maybe you just didn't see it right, or I don't know, you were confused or something. You switch those around. So all of this stuff is going to be switched around, right? So then all of this stuff is going to be messed up. This stuff is all going to be messed up. But if you did what Johnny did, and you basically made that one little mistake at the start, but then you did everything else right, you're going to get this. So let's talk about what you do in this situation. Actually, can we talk about what you don't do? Yeah. Or worse yet. That's way worse, right? Because you just told me a total lie. That's not true. That's not true at all. So that's really bad. There are some ways you could handle this, perhaps. I think, Johnny, you said this. You just threw in some absolute values. I mean, to me, this is like that statement is true, but like I would have to question, like, hey, dude, why the absolute values all of a sudden? Right? I mean, it's just like a fashionable way to finish, or you know what I mean? Like, there's no rhyme or reason why you would do that. Can I show you what I feel like is the most efficient way to do this? Hang on one second. I think the most efficient way to do that is this. I would say, therefore, the area is 4.5. I haven't equated -4.5 with 4.5. I've basically just said, oh, area has to be positive, and I feel really comfortable with all my numbers, but maybe I realized I flipped things around. I'm going to fix it by just saying, okay, therefore the area must be 4.5. You could even say, I think I flipped around the integrand's order a little bit, so I think the area should be 4.5 or something like that. Totally fine. Or couldn't you go back and reintroduce some absolute values at the start?
Yeah.
If you got to that point and you're just like, oh no, negative area, never good, couldn't you go back through and say, well, why don't we just absolute value this difference, right? Like you flipped it around, right? So, I mean, I wouldn't technically need to do this. It wouldn't hurt mine at all. It wouldn't actually change mine. So then we'd do this and this and this, such and such. And then you could then go, think 4.5, right? So you want to deal with it correctly, but hopefully not have to erase and redo the whole thing. I personally am a fan of just saying, oh, therefore the area must be 4.5. Something like that.
But I would still probably get a point off in the very beginning for the incorrect integrams. Wouldn't I?
No.
No?
No. You would not. If you navigated that correctly, you'd get full credit. So yeah, Jackson asked a great question. I think it's worth asking. He said, "Could you just use Math 9 on this thing, or because once you set it up, done?" I would say no. It would not be calculator active. I'm going to show you an example of that here in just a moment. But I think what I'd probably do, like if I gave you a question on a quiz like this, I'd probably give you the graph, and I might even give you the intersection points. Just from a time perspective, I think that makes sense. But then I'd say, all right, no calculator. Can you set this thing up and execute all the way through? So probably not. But if the calculator is active, wouldn't you be foolish to not use Math 9? I think you'd want to do that for sure. All right, so guys, that's it. Unless you have another question. Okay. Man, time goes by way too fast.